Let us begin with our first topic, which is linear dependence and independence of vectors. So vectors are nothing but rows or column matrices. That means if we are considering a row matrix like this, A, B, C, or a column matrix like this, 1, 2, 3. So these are nothing but rows or column vectors. Now we have to talk about the linear dependence and independence of these vectors. So for this, suppose I am considering capital X1 is equal to 1, 2, 3 and X2 is equal to 2, 4, 6. Then from X2 what we can observe, that we can take 2 common from this matrix 1, 2, 3. So this X2 can now be written as X2 is equal to 2 times X1, or 2X1 minus X2 is equal to 0, or null matrix O. So from this what we can observe, that one vector X2 can be written as scalar multiple of other vector X1. So here we are taking 2 to be the scalar. So in this case we will say that the two vectors X1 and X2 are linearly dependent. So from this, how we can define linear dependence and independence of vectors? Two vectors X1 and X2 are said to be linearly dependent if one can be written as scalar multiple of other. And if this happens, then we will have a relationship between the two vectors X1 and X2. Now this is about only two vectors. Now what if we are given more than two vectors? So for that we will define what do you mean by linear dependence and independence of vectors. So now we will define what do you mean by linear dependence and independence of vectors for n vectors. So let x1, x2 to xn are n vectors of same order, and let there exist scalars lambda 1, lambda 2 up to so on lambda n, not all 0, this is very important, not all 0, such that lambda 1 x1 plus lambda 2 x2 plus and so on lambda n xn is equal to 0. Then we will say that the vectors x1, x2 to xn are linearly dependent. Okay. As we have seen in the previous example, 2x1 minus x2 is equal to 0. We have got this relation. So you can compare this with this definition, that two vectors x1 and x2 are said to be linearly dependent if there exist scalars 2 and 1, and definitely they are not 0, such that lambda 1 x1 plus lambda 2 x2 is equal to 0. Then we will say that the two vectors x1 x2 are linearly dependent. So here we have got lambda 1 is equal to 2 and lambda 2 is equal to minus 1. Okay. Now if all the lambda i's are 0, what I am saying, if all the lambda i's are 0, then we will say that the vectors x1, x2 to xn are linearly independent. That means if we are considering this relation, 0x1 plus 0x2 is equal to 0, then again this equation is correct. But here both the scalars lambda 1 and lambda 2 are 0, and therefore x1 and x2 are linearly independent. So let us consider our first example. The question is, check whether the following set of vectors are linearly dependent or otherwise. If linearly dependent, find the relationship. That means we have to check whether the set of vectors x1, x2, x3 are linearly dependent or linearly independent. And if they are linearly dependent, we have to find the relationship. So as we have seen here, that if the two vectors x1 and x2 are linearly dependent, then only we can have a relation between these two vectors, lambda 1 x1 plus lambda 2 x2 is equal to 0. And if the two vectors are linearly independent, then there is no question of relationship. So in this type of example, what we have to do, we have to first assume that the vectors are linearly dependent. That means we assume that let there exist scalars lambda 1, lambda 2, lambda 3 such that lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 is 0. That means we are assuming that lambda 1 into x1 1 1 1 3 plus lambda 2 into 1 2 3 4 plus lambda 3 into 2 3 4 7 is equal to 0. 0 is nothing but a null matrix which will be of same order as the order of these vectors, because we have equality here and the two matrices can be equal only if first of all they are of same order. So now from this equation we can write this as, so these are nothing but matrices and we have to take the sum of the matrices by taking component wise addition. So it is like this: lambda 1 plus lambda 2 plus 2 lambda 3, this will be the first component. Then lambda 1 plus 2 lambda 2 plus 3 lambda 3, this will be the second component. Then lambda 1 plus 3 lambda 2 plus 4 lambda 3, and the last component will be 3 lambda 1 plus 4 lambda 2 plus 7 lambda 3, and this is equal to what? 0 0 0 0. Now if the two matrices are equal, then each and every corresponding element should be same. So this will give us 4 homogeneous equations like this: lambda 1 plus lambda 2 plus 2 lambda 3 is equal to 0. Then lambda 1 plus 2 lambda 2 plus 3 lambda 3 is equal to 0. Then lambda 1 plus 3 lambda 2 plus 4 lambda 3 is equal to 0, and at last 3 lambda 1 plus 4 lambda 2 plus 7 lambda 3 is equal to 0. So we have got the 4 homogeneous equation. Homogeneous means right hand side is 0, and now we have to solve these equations. Suppose this is 2, 3, 4 and 5. We can take this as equation number 1. So what we have to do, now we have to solve any two of these 4 equations by using Cramer's rule. So what is Cramer's rule? Suppose we are given two equations, a1x plus b1y plus c1z is equal to 0 and a2x plus b2y plus c2z is equal to 0, and you have to find the values of x, y, z. So by Cramer's rule, it is given by x upon, so you have to hide the terms of x and you have to write the coefficients of y and z in determinant form. So it is b1 c1 b2 c2. You have to take the determinant of b1 c1 b2 c2, and this is equal to minus y upon, again hide the value of y and consider the determinant like this: a1 c1 a2 c2. And in the similar manner, z upon, hide the values of z and consider this determinant a1 b1 a2 b2. So this is how we can obtain the values of x, y, z. So remember, we are taking here x positive, then y negative, then z. So plus minus plus. So coming back to this equation, we are considering the two equations, second and third, and we will solve it using Cramer's rule. So we will have, it is lambda 1 upon, hide the values of lambda 1, and you will be getting the determinant of 1, 2, 2, 3. Then this is equal to minus lambda 2 upon, again hide these values, 1, 2, 1, 3. And then lambda 3 upon, hide the value of lambda 3, then it is 1, 1, 1, 2. So what we are getting here, it is lambda 1 upon, it is 3 minus 4 minus 1 is equal to minus lambda 2 upon 3 minus 2 1 is equal to lambda 3 upon 2 minus 1 1. So from this we can write the values of lambda 1, lambda 2, lambda 3 is lambda 1 is equal to minus 1, lambda 2 is equal to minus 1 again, and lambda 3 is equal to plus 1. Or this can also be written as lambda 1 is equal to 1, lambda 2 is equal to 1, and lambda 3 is equal to minus 1. So we have got the non-zero values of lambda 1, lambda 2, lambda 3, but these values are obtained using only equation number 2 and 3. We have to verify that are these terms of lambda 1, lambda 2, lambda 3 are satisfying equations 4 and 5 also or not. If one of these four equations is not satisfied, then we will say that the vectors are linearly independent. So put here lambda 1 is equal to 1 in equation number 4. So we are getting here 1 plus 3, 4. 4 minus 4 is 0. Yes, we are getting it. And if we are putting lambda 1 is equal to 1 here, 3 plus 4, 7 minus 7 is equal to 0. So these values of lambda 1, lambda 2, lambda 3 are satisfying equation numbers 4 and 5 also, and therefore we will say that these are our required lambda i's. So since these values of lambda 1, lambda 2, lambda 3 also satisfies equations 4 and 5, these are our required scalars such that lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 is equal to 0. Therefore, vectors x1, x2, x3 are linearly dependent, and the relation is we have to write the relation from equation 1, which was our assumption. So it is lambda 1 x1 plus lambda 2 x2 minus lambda 3 x3 is equal to 0. So this is our final answer.